Welcome everybody to our second video. Today we're going to be talking about 1.2, which is how do we evaluate limits algebraically? And so really we're going to be answering this question, how do we evaluate limits without using a graph? In our previous video, when we introduced this concept of limits, the simplest way to think about it is to be able to look at a graph and see, okay, where is my y value going as my x approaches a certain x value? What if we don't have a graph? Well, I want to remind us of a concept that we talked about in the previous video, starting out with a nice simple example like we did before. So let's say I want my limit as x approaches 3 of the function x squared minus 4x plus 7. Okay. Well, what do we notice? This is just a nice quadratic function, right? If I think about its graph, I know its graph is going to be a parabola. Since this is just a quadratic function, do I have any discontinuities? No, there are no discontinuities for this function, which means the function's continuous at 3. Well, what did we talk about in our previous video? If my function's continuous at a point, I can just plug in the function value in order to get what the limit is, right? So this is the same thing as just if I take my function and plug in the function value. So if I do that, I get 3 squared minus 4 times 3 plus 7, which gives me, I think, 4. 9 minus 12 is negative 3. Negative 3 plus 7 is 4. Okay? So this concept we're actually going to be using a lot today. Okay? And so let me formalize this a little bit more. If a function, I'll go ahead and give it a name. Not that every function is going to be f of x, but if some arbitrary function f of x is continuous at some x value, and we'll just use c to represent any arbitrary x value. If a function is continuous at x equals c, then the limit as x approaches c of that function, what did we say? If it's continuous there, the limit matches what the function value is at that point. All I have to do is just plug in that x value. Okay? Furthermore, that means, if this is true, that means the limit exists, right? And if the limit exists, that means if I approach from different directions, what should be true? I should get the same thing. If I'm getting different things from different directions, then the limit without a direction specified won't exist. Okay, we're gonna talk about that more later too, just so we'll get that reminder. Okay, so that's my formal limit definition of a continuous function or continuity. Okay, so we're going to use that as we get into how we evaluate different functions. So to be clear, today we're going to be focusing on functions that only have one rule. So we're not going to be talking about piecewise functions. We talked about piecewise functions at the end of the last video of how we can evaluate those limits algebraically, right? Because with piecewise functions, it's either continuous or we have a jump. So all I have to do is just evaluate each of the different rules separately to see if the point where the rule changes is a jump or a continuous point. So today we're going to be focusing on wholes and asymptotes. Okay, deciding whether a function has a discontinuity of a whole or a discontinuity of an asymptote at a specific x value. Okay, so let's start with a nice simple function here. Let's look at the limit as x approaches 1 of 7 over x minus 1. Okay. So some of you guys might already see, oh yeah, this one's not continuous at 1. But what if I couldn't see that just right off the bat? What if I looked at this and I said, I don't know if that's continuous or not. Well, let's just assume that it's continuous. Let's start out by assuming it's continuous. If it's continuous, then my limit is just going to be whatever the function value is. So let's go ahead and plug in. Let's plug in 1, see what we get. So I plug in 1, I get 7 over 1 minus 1, which is equal to 7 over 0. Okay, so sure enough, when I plug in 1, I get 0 in the denominator, which hopefully you know by now is a big mathematical no-no. We don't want 0 in the denominator. So, sure enough, I have a discontinuity at x equals 1. But this wasn't a waste of time. This still tells me something. What does it tell me? This tells me that as I let x approach 1, this tells me that the numerator of my fractions, because I'm working with a fraction here, right? My numerator is approaching 7. Okay, and in this case, it's not actually moving at all. It's always 7, right? It's constantly 7. And my denominator, what is my denominator approaching? I spelled denominator wrong there, but that's okay. My denominator is approaching 0. Oh, interesting. So my numerator is staying constant at 7, but my denominator is getting infinitely close to 0, which means your numbers are getting infinitely small. Infinitely small. What happens to a fraction if you let the denominator get smaller and smaller and smaller? Well, it turns out the fraction as a whole is going to approach some infinite value. If your denominator gets infinitely small, the number as a whole gets infinitely large. Right? Think about 7 over 0.1, 7 over 0.01, 7 over 0.001. As I let that denominator get infinitely small, my number gets infinitely large. Okay, so this tells me that my function value is approaching some infinite value. So I'm not working with a whole here. I'm working with an asymptote. Okay. Well, we have to be careful because it doesn't necessarily approach positive infinity. I know I wrote positive infinity, but all this tells me is that it approaches some infinite value. In order to figure out whether it approaches positive infinity or negative infinity, I have to look at both directions. So let's look at approaching 1 from, and this time we're going to start with the positive direction because that one's a little bit more straightforward. So let's approach 1 from the positive direction. That means I'm approaching from numbers slightly bigger than 1. Of course, the numerator is not changing. But what's happening in the denominator? If I'm approaching from numbers slightly bigger than 1, then what happens when I take that number and subtract 1? I'm still approaching 0. I'm still approaching 0 here. But I'm approaching from numbers that are positive. I'm approaching from numbers that are positive because any number I plug in that's greater than 1 is going to give me a positive value in the denominator. 1.1 minus 1 is 0.1. 1.01 minus 1 is 0.01. So all of my numbers, as long as I pick numbers greater than 1, are going to give me a positive value in the denominator. What does that tell me? That tells me that this approach is positive infinity because both the top number and the bottom number are positive. If I switch this and approach from numbers less than 1, I get something similar. If I approach from numbers slightly less than 1, that means I'm working with numbers like 0.9 or 0.99, right? Slightly less than 1. If I take that number and subtract 1, I'm going to end up with a negative value. I'm still approaching 0, but I'm approaching 0 from values that are negative. I'm getting infinitely small, but it's negative numbers that are getting infinitely small. What does that tell us? That tells me that my limit is negative infinity. So that means I do have an asymptote, but it's one of these asymptotes that, here, what are we working with? We're working x equals 1, that goes up on one side and goes down on the other side. Okay? What does that tell me if I just put the limit without a direction specified? What's this limit equal to? This limit does not exist because you don't get the same thing if you look at either direction. The limit coming from either directions don't agree. They're not consistent. Awesome. Okay, let's look at another example. Okay, let's look at the limit as x approaches 3 of x cubed minus 27 over 3 minus x. Okay, so once again, you might be able to quickly see, yep, I've got a discontinuity here, but I would still tell you, first step, assume it's continuous and plug in the value. See what you get. Okay? Because like we said in this previous, or like we saw in this previous example, plugging in the value still helped me. It still helped me get to a good idea pretty quickly that I was working with an asymptote. So let's plug in the value, see what we get. Okay? So I'm going to plug in 3 cubed minus 27 over 3 minus 3. And I get 3 cubed is 27. So I get 0 over 0. Interesting. What does that tell me? Well, first off, it tells me, yes, I have a discontinuity at x equals 3. I'm working with either a whole or an asymptote. Remember, it's not a jump because I'm not working with a piecewise function. Which one is it? Whole or asymptote? Well, what this tells me is I let x approach 3, then the numerator is approaching 0, and the denominator is approaching 0. So is my number getting infinitely small, infinitely large? Well, it turns out this is what's called an indeterminate form. What does that mean? That means it doesn't tell me enough information. It's not enough information. I cannot make a conclusion based off of 0 over 0. I don't know if it's a whole or an asymptote. Okay. There are more indeterminate forms when we're working with limits. It turns out if you end up with infinity over infinity, it's also indeterminate. It's not enough information. If you get infinity times 0, that's also indeterminate. Okay. And infinity minus infinity is indeterminate. So those are my 4 indeterminate forms. And if you run into that while you're working with limits, you don't have enough information, and you have to. I have to do more work in order to figure out what this limit is equal to. Okay, so that does right. So like I said, that doesn't mean I can't solve this. That just means I have to do a little bit of algebraic manipulation in order to get it to a point where it is conclusive. Okay, so let's go back to my original limit. Is there some way I can algebraically manipulate this to simplify it a little bit? Well, it turns out, let me switch to black. It turns out that the numerator can factor. I can factor the numerator. So when I factor the numerator, I get x minus 3 times x squared plus 3x plus 9. Well, I can also mess with the denominator a little bit by just multiplying it by -1. Okay? Or what I'm actually doing is I'm actually pulling out a -1. If I pull out a -1 out of the denominator, I get -3 times -1 gives me +3. So I get a -3 plus x. Are we okay with that? Right? -1 times -3 is +3. -1 times x is -x. Well, the reason why that's important is -3 plus x. I can rewrite that as x minus 3. What do we notice? Right? By factoring, I was able to figure out that both the numerator and the denominator have a common factor. They have a common factor of x minus 3, which common factors can cancel out because they divide to equal 1. What's happening with this function is those two factors will constantly be dividing to equal 1, except for that very specific case where x is equal to 3. So that means that this function acts very similar to the function just x squared plus 3x plus 9 over negative 1. Well, if you divide by negative 1, it's the same thing as multiplying by negative 1. So negative x squared minus 3x minus 9. Okay? Since these functions act similarly, it turns out that the limit of my original function is I now know that the limit is going to be equal to the limit of this more simple function. Okay? Well, how is that helpful? Remember, all these are negative because I divided by negative 1. How is this helpful? Well, if I go back to what we talked about initially, if I end up with a function that's continuous at the point, all I have to do is just plug in the function value. Take a look at this. I got rid of my discontinuity. So this now is a continuous function at x equals 3. It's actually always continuous. And so, to finish up, all I have to do is plug in the function value, or plug in the value. And I get negative 3 squared minus 3 times 3 minus 9. And I end up with negative 27. Now, to be clear, this is not the same function as this. Those are two different functions, but they act similarly. They act the exact same, and that's why their limits are equal. And so, now I'm able to get out just negative 27. What does that tell me? What type of discontinuity is this? This ends up just being a hole. Because my limit exists, it goes to the same point on either side. The reason why I know it goes to the same point on either side is because I ended up with a continuous function. And continuous functions, I know that they go to the same point on either side. Okay? Now, just because you get 0 over 0, that does not mean, you might think after this example that, 0 over 0 means you get a hole. Not necessarily. That's why it's an indeterminate form. If I go through this last example real quick, we can see why this isn't the case. If I take a look at the limit as x approaches negative 1 of x squared plus 5x plus 4 over x squared plus 2x plus 1. If you plug in negative 1, you're going to get 0 over 0. Okay? But when I factor this, I get x plus 4 times x plus 1, and then x plus 1 over x plus 1. X plus 1 times x plus 1. So sure enough, I have a common factor, and I can cancel out that common factor with one of the common factors in the denominator. So the limit of my original function is equal to the limit as x approaches negative 1 of just x plus 4 over x minus 1, or over x plus 1. But notice, did I get rid of my discontinuity? If I plug in negative 1 right now, I still end up with 0 in the denominator. So I still have a discontinuity. And what does this tell us? This tells me I'm not working with a hole anymore. I'm working with an asymptote. Okay? If I try going from either direction, I'll see that one goes to positive infinity, the other goes to negative infinity. So it turns out this limit does not exist. Because one goes to positive infinity, the other goes to negative infinity. Okay. So that's how you can evaluate limits without a graph. And it boils down to just plug in the value, see what happens. if you get an indeterminate form, do some algebraic manipulation to get to a point where you don't get an indeterminate form. Okay? And I'm pretty sure with almost all the problems on the homework, it's just going to be this factoring of a polynomial. It'll just be factoring a polynomial. Okay? Okay, try out the homework. If you have any questions, let me know. Thanks, guys.